8.1, revisiting domain. Remember, your domain is your x values, right? Especially if we're looking at x and y values. And since we have gone over functions, remember that functions, that's f of x, that's the same thing as like a y type thing, but the x's are still x's, okay? And once again, domain is related to x type values. When we list these in like a set builder notation, which I think we'll see today, but you got some fancy brackets. Remember, we got the s and the 2. And then sometimes you just kind of list out the x values. So you close them with some fancy brackets. There's a 2 and then an s. Set builder notation says, well, you're dealing with x's, and then you got to declare what those x values could be. It says from 2.6, but I think it was more from module 7 kind of stuff, right? Where you saw some, whatever. Maybe it was 2.6. But in any case, below is the formal definition of a function. It's really just a nerdy way to say, for functions, remember every x value, you can only have one corresponding y value. You can't have, for example, in a set, you can't have the ordered pair 2, 3, and then also have the ordered pair 2, 10. Because, and we talked about this is like your input, right? Your x values are input. When you put it in a 2 and you get out a 3, that's good. But if you come back and you put it in a 2, and now comes a 10, it's like, what the crap is going on right here? And then it's no longer a function, okay? And there's different ways to do that, both with equations and tables and mappings and graphs, but that's really what it comes down to. So this particular lesson is mostly about domain. So yeah, there's just a quick explanation that we saw about range as well. You know, now that I think about that more, I think it was 2.6 that we saw domain and range stuff, but I also assume no one really cares. But in any case, there's your domain stuff. Yeah, domain, a list of the x values. We know we saw in the beginning there, sometimes that requires some of those fancy brackets, which are super awesome because they're so fancy and classy. When solving equations, we ended with one answer. Yeah, that was just like this one right here. This is the one-step equation. We did two-step equations, then multi-step equations. That's principle of equality stuff, in addition to distribution and combining like terms, okay? But in the end, we found only one value. Most of the time, we only found one value of x that would make the equation true. That means that there's only this one value in this particular equation in the domain. Now, later on, we saw absolute value equations that could have had two answers, and then you'd say, well, x could be maybe 3 or 14, I don't know. And then now you'd have two values in the domain. But we even saw sometimes where the equations had an infinite number of values. And there are different ways to express those, even if they're within some kind of interval. And there's that dreaded, awesome word that we remember, intervals, because they are coming back when we talk about domain. And so sometimes we're going to actually, oh, there it is. Oh, no, I was thinking infinite. Some of these we're going to have to describe with intervals, okay? Yeah, and with regular graphing, y equals mx plus b stuff, remember m is slope, b is the y-intercept. Hopefully you kind of remember that because the final's coming up. But there's an infinite number of x values. If you look at a graph, right? So let's pretend like these are good lines. That's an x-axis and a y-axis. If you drew some kind of line with y equals mx plus b, kind of thing, you got the y-intercept and then the slope is m. This, I probably should have put those arrows on there, but this line continues forever to the left and right. And remember, that's all we're concerned about with domain. That's our x values. So this would go from negative infinity, it would never stop, and it would go all the way to positive infinity as well. Okay, so that's kind of what we focused on, is seeing what values of x do work. Really, what we're going to be looking at today is values of x that don't work in the equations, right? Now, that doesn't mean we're going to include those in the domain. We only want to include values of x in the domain that make the equation true. Okay, but sometimes it's easier to figure out what those values are when you think about what x is not. Okay, so this is more of what's called indirect reasoning, like when it comes to logic and stuff like that, okay? So we're looking at everything that would not work, and then that kind of tells us in response what would work. I don't know, that can be kind of confusing, but we'll see some examples. Hopefully this would make sense as we see some examples here. And yeah, like I said, we're going to be using some interval notation, which is either one of these. Remember, if it's included, we use a square bracket. If it's not, then we use just regular parentheses. On graphs, the square brackets like this, that was the closed circles, and then the regular parentheses, those were the open circles, okay? And again, that's since we're only dealing with X numbers, we tend to use the horizontal number line like this one, right? Then you got positives to the right, negatives on the left. And then, yes, so for example, right, you could say, maybe we see in something like this, right? So maybe one's open, one's closed, and then just whatever's between those. And the domain is gonna say, maybe the domain, the only values of X that would work in this particular equation, whatever it is, would work only in this interval. And then, yeah, set builder notation now, so we know it's always X is, and such that X, maybe it's less than, maybe it's greater than, maybe it's less than or equal to or greater than or equal to, but usually includes some kind of inequality in here to demonstrate the interval that would work as well. On Canvas, usually all you gotta do is type in this part, like this. Now, if you did, just by chance, if you did need to, the fancy brackets, they're on the, I don't know, they're close to the enter button right there. Yeah, and so that's the fancy brackets, but this line right here,
Yeah, that.
you know, X is such that, whatever this symbol means, it's usually like one button above return. And I'm looking at my iPad, it's the same thing as my computer, which is, what do they call it, PC or whatever. Let's look at domain of root functions, okay? So even roots cannot have negative radicands. Remember the radican's on whatever's on the inside of the root. So if we see some kind of root like this, whatever's in here, and sometimes it's an expression, right? Like we see in that maybe be x minus 3, something like that. Maybe x minus 13, maybe 4x minus, whatever it is, okay? But the interesting thing about this is that your radicand, remember, we can't have a negative radicand because you wouldn't want a negative area for a square. Or you could say, well, what number, let's look at an example here, okay? Let's go back. So if we said, we're gonna take the square root, let's make it, well, let's actually start with 9, just 9 for now, okay? So this is really asking what number times itself is 9? And then we would know that's 3. And if you don't, your calculator does, okay? Now, if we put a negative on that, the question is, what number times itself is negative 9? Now, again, one of the common mistakes while we're getting used to this stuff, and we did just finish Module 7, so students will say it's negative 3 times negative 3, but that's not negative 9, that'd be positive 9. Remember, they have to be exactly the same number, and of course 3 times 3 is positive 9. So this is where we say, right now we're just saying that the answer is not real or DNE kind of stuff, right? But when it comes to the domain of these root type functions, what we're saying is that whatever the radicand is, it has to be greater than 0. So if we looked at this example, this first one that we started with here, I don't really care about the radicand so much, I don't care about the root so much as the radicand, the inside right there, right? So that's when I say, I'm just gonna take the inside of the root, the radicand there, 4x minus 13, and I just know it has to be greater than or equal to 0. I can solve this inequality, like we saw on the last slide, I can put that into set builder notation, I could put that inequality on a graph, and then I could write the interval for that inequality as well. I'm not going to solve this one because we're going to have plenty to solve. But this is essentially what we're doing. Just take the inside of your radical, in this case the root, and just make it greater than or equal to 0. Now remember, this is only when the index is either not shown or if it's even. If it were an odd index, then none of the inside matters. That you could have whatever value of x you want, and you could pull out whatever the root is. Okay, again, this is only applying to even roots. All right, find the domain in interval notation. Okay, no problem. Now I'm going to put the graph on this one just to give us a little bit of a reminder on that stuff. Not just because it's going to help me to make the interval, but it should help us with stuff that may be on the final, right? So once again, all I'm going to do here, let's take a closer look. I'm just going to take the inside, this 3x minus 4. And I know that it has to be greater than or equal to 0 in order for us to have any real values out of this radical, this square root, okay? So this right here actually does represent the domain, right? But I do want to solve this so I can figure out exactly what values of x would make this work, okay? So here's where we come into some principles of equality. Right here, I'm going to add 4 to both sides. That's going to zero that out, drop my 3x, which now is greater than or equal to 4. And then finally, with a little bit more space, I would divide both sides by 3, okay? So I see x must be greater than or equal to 4/3. That is the domain. Now, if this is set builder notation, maybe you got some fancy brackets, s then a 2, to close them, it's a 2, then an s, and we'll say x such that x is greater than or equal to 4/3. Now, this is nice, and it was fun to do, but if that coefficient were a negative, remember with your inequalities, if you ever had to divide or multiply both sides by a negative, it would have flipped that inequality, which could happen now, just like it has happened in the past, okay? So this is set builder notation, but it said it wanted interval notation, right? So let's make sure that we put this in interval notation. And again, just as a nice review, let's look at the graph on this one. So right in the middle, I'd have 4/3. To the left of that would be 3/3, and then to the right would be 5/3, okay? This one is x is greater than or equal to 4/3. It's equal to 4/3, could be. So I got a closed circle there at 4/3. This one is eating the x, which means that the line should go to the right. And now that's all that I would need from the graph, but now I need the interval notation starting at 4/3, which is included. So I got a square bracket there. This goes all the way to infinity, which is never included. So there at the bottom, we have square bracket 4/3, and then it goes all the way to infinity with closed parentheses. That right there is the interval. That's the domain. And yeah, you can say domain with that kind of stuff, but either way. Question. So right here, I always set it up with the 0 on the right side of the inequality. And it should always be opposite of I'm saying opposite, it should not eat the 0. Or you could say that it eats the radicand, right? So another way to set this up would have been 0 is less than or equal to 3x minus 4. And that would have worked too. If you solve this, you'll get the exact same inequality, just maybe your x is on the other side. So you'd end up with x here, but 4/3. But again, it would be eating the x like this. All right, you guys, for this one, for those of you that remember in class, I did this one in class, but remember I kind of started this by looking and seeing, because of the trinomial, I was looking to factor this out, right, and then solve this from here, and then I broke it up like this. I was doing kind of a different problem, and the final result is just negative infinity to infinity, because it doesn't matter what's on the inside here with the index being an odd number. You can have any value of x and get something out of it, okay? You're not going to get any non-real values out of this function, so the domain would span from negative infinity all the way to positive infinity. We didn't need any of this stuff, okay? So instead of keeping that part of the recording, I'm just explaining what I did in class and how I made that mistake, but hopefully you don't make the same mistake. Just look at the index there, it's odd, boom, negative infinity to infinity. So now we're looking at fractions, because it's talking about denominators here. Remember, in a fraction, the top value is the numerator, the bottom one is the denominator. We're only focused on the denominator. That's it. I don't care what the numerator looks like. It could look really big. It could look complicated. I don't care what the numerator looks like. All I care about is that denominator, okay? And here's why. Because if you look at fractions, and we've seen this, if not here, then hopefully maybe in some other math class, if you ever see a denominator that's 0, what we end up with is something that's undefined. Maybe I should give myself more space. Let's see if we can fit this undefined. It's undefined, okay? Now, undefined values, we can't say that those are part of the domain, which is why in the past when we've seen them on our inequalities, we don't actually include them we never include those with square brackets. And when we say undefined, we're talking about infinity, okay? And so, I kind of feel compelled to say why it's undefined, why it's infinity, okay? Let's take 1, okay? How much of nothing is in 1? Now, some people would say, just without thinking about this, there's only 1 in 1. That's true, but how much of nothing is in 1? See, well, there's 1 of nothing. Okay, that's true. How about a gazillion nothings. Would that satisfy one? No. So you see how this goes pretty quickly up to infinity when you divide by 0. Okay, so, you know, there's that picture of some kind of gaping hole in a house when you divide by 0 or something like that. Whatever. It's just saying that it's undefined. Mathematically, we can't quantify how much of nothing is in something. Okay. So, you know, if you want to speculate about that, that's fine. So, now we have to be able to skip these numbers. Okay, so let me, I can't skip the part right there, okay? So in your denominators, you're going to end up with more of these expressions, right? Maybe it's something like x squared minus 1. Okay, all we know is that whatever the x value is, it just can't make that full denominator equal to 0. So whatever it is, what we do is we say we're going to look at it equaling 0, but it just can't equal 0. And so that's why you put the slash sign through the equal sign. Okay, it's just not equal to 0. And again, whatever's in the numerator here, I don't care what's there. I'm only focused on the denominator. Now, some students are like, well, what if there's x's in the numerator? I don't care. I don't care what's in the numerator. I don't care what it looks like. All I care about is the denominator. And then you can break this up and say you're going to figure this out. We solve these pretty much like we would an equation, but again, it's just that it's a not equals. What this does is it tells us values of x that would make the denominator 0, which then would not be included. They would not be included in the domain. All right? I know this one, I don't know that we're going to see anything like this. We could. But we already know how to solve these types, okay? In any case, I don't expect that we're going to see any squared x's. But again, the idea when we put these into interval notation is we have to be able to skip the values that would make the denominator 0. Again, if we're just looking at replacing the x with 0 in the denominator, to make its full value 0, we have to be able to skip those x values. I feel like I'm talking in circles here. So let's look at an example. Hopefully this will help, okay? So I got g of x equals 16 over x minus 15. Now, as I stated before, we don't care about that 16. And you may think that's insensitive, but I'm a math person, so I don't care. Okay, so maybe that's insensitive. But in any case, x minus 15, again, we want to look at when it equals 0, but I'm going to put a slash for that. And I think my slash goes the other direction, but I don't care because it's just a slash, okay? It's just saying that it's not equal to 0. I just want to know when x minus 15, I want to make sure it does not equal 0, right? So to solve this, I'd say let's go and add 15 on both sides. Okay, now if this happens, I get that zeroed out, I drop my x, now it does not equal 15. Okay, so as long as x does not equal 15, then I can get a true statement out of this, some kind of real number out of this function, okay? Now that would be kind of what we would call the inequality here, but we don't want the inequality, we want the interval notation. So how do we demonstrate that 15 will not be included in the interval? Well, the graph I think will help. Okay, so let's look at the graph. Okay, so you got positives to the right, negatives to the left. I'm going to put 15 right in the middle, and then of course 16. I think I did this one correct, and then 14. Okay. So x cannot equal 15. That means it can't be included. That's an open circle at 15. Well, what does that say about all the other values of x? That means that they're okay. So everything to the left of this 15 and everything to the right of 15 is good. So there's my arrows. So think about what the domain would look like just for the green part of this. And we have to be able to skip that 15. Well, I can see to the left that would go all the way to negative infinity. It's going to stop at 15, which is not included. So there's a closed brackets. And then I will unite this starting again at 15, but it's just not included. And then it will go all the way to infinity. So we get some kind of OR statement in here, a union statement with this interval. But you see that it matches the same number. That's because it's not included in either interval. Okay, this is how you skip just individual numbers with interval notation. Yep, so let me address that here real quick. Let's say that maybe 16 wasn't included. Then you'd have to have an interval from 15 to 16. And then you'd have a second union. Maybe I shouldn't have said that. But that, just so you know in the future, because that will happen, they're gonna give you little intervals like that as well. But this one's good. This one's good. We can stop right there. So 12x plus 45 all over 4x plus 7. This is f of x. It's our function. And again, I don't really care about that numerator. There is an x there. I just don't care, all right? And you could even say, maybe we could factor something out of that. I don't care. All I'm focused on is that 4x plus 7. That's it. Well, you know what? You guys take a minute and try this one out, and then we'll go over it. Now, hopefully that was enough time then. Now, once again, I don't really care about that numerator. I'm just focused on that denominator, 4x plus 7. Again, it just, whatever it is, it just can't equal 0, because then it would get something that's undefined. So let's solve this one just like, again, we would a regular equation. So I'm going to subtract 7 from both sides. That's going to zero that out. Let's drop the 4x, which now equals negative 7. And then we'll divide both sides by 4. And this tells us, well, I guess I forgot my slash, but x cannot equal negative 7/4. Okay? So once again, if we were to look at the graph, wherever negative 7/4 is, we'd have an open circle there. But everything to the left of negative 7/4 and everything to the right of negative 7/4 would give us some kind of value out of this function. And remember, it's the denominator that's 0. If you're wondering, well, what about if the numerator is equal to 0? That's fine. We don't really care about that, but it's just in the denominator, okay? So for our interval, this purple line, it goes all the way to negative infinity. It's going to stop at negative 7/4. That's not included. So again, we got the closed parentheses there. We'll unite this. Once again, starting at negative 7/4. Not included. So go all the way to infinity. Also not included. So yeah, there's our interval right there. I think that's an important question because remember with inequalities, it was kind of what values make the equation or the inequality true. This one is just saying what values can exist in this function. And so, of course, we kind of expect there to be a lot of values. And then with the square roots, then it's just, yeah, so for this one, right, with the denominator stuff, we're just looking at not equals to one number. Maybe if it was some kind of trinomial or something like that, we'd look at 2. But it's not. And then with square roots, it's just greater than or equal to 0. Let's look at that in a couple different ways. Okay, so let's say that it wanted the domain of f of x equals maybe even just 1/2 like this. Okay, and that just would be a number. It's the same thing as if you were to say f of x equals, I don't know, 5. It could be negative as well. Okay, so it would say, well, what values of x are good to use in this function? All the values of x for this one, for both of them. Okay, it would say, look, no matter what value you use in this function, either one of these, you'll never get some kind of undefined value out of that. So the domain for problems like these ones, and again, even if it's a fraction, again, we're only concerned with that if there's an x in the denominator, then we would have to worry. Okay, but even if, we'll make this one nice, but yeah, if it's like a square root right there, it still keeps the same domain. Now, again, if this was negative, then it's a whole different story, but if it's just a value, then we're good. So let me demonstrate just like f of x equals negative 5. Because remember, this really is the equation y equals negative 5. And so what does that look like on a graph? Well, it would be like having a line here at y being negative 5. And you can see this line for the x's, it goes all the way to negative infinity, all the way to positive infinity, just like the square root of 1/2 would, or even just 1/2. All right, so for this one, once again, and it's still a function, it's just y equals something right there. But again, I don't care about that 15, just 26 minus x. It just can't equal 0, that's all. All right, now this one I'd say, well, let's go ahead and subtract 26 from both sides. And I think some of you could probably even solve this without doing the principles of equality, whatever's good. And so I'm going to drop, now remember on this one, I think this is a good review. Make sure you drop this as negative x. You can even say it's a negative 1x, okay? But it can't equal negative 26. Finally, to solve this one, I'll divide both sides by negative 1, and that shows me x cannot equal positive 26. Okay, so once again, let's look at that graph. So right at 26, so to the left would be 25, to the right is 27. We'd have an open circle there at 26. Everything to the left is good, everything to the right is good. So the green lines, that's what we're looking at, that's our domain. Goes from negative infinity to 26. It's not included. we'll unite this starting at 26. Not included still, though, goes all the way to infinity. But infinities are never included, so that's our domain. So problems like this one, this is kind of like the root thing. I'm not gonna overcomplicate this one. Just, if you get, doesn't matter if you got x squareds or x's, whatever you got in this, something like this. You could even look to factor it, but it's not gonna make a difference. This one just goes from negative infinity to positive infinity. Again, this is just a domain question, right? We're not asking what values of x, or if you replace x with some value, what value you get out of it, right? Input and output kind of stuff. We're just saying what values can you put into x and still get some kind of value out, some kind of real value out. And yeah, anything but negative infinity and positive infinity will work. You could even say, look, I'm gonna replace the x's with zeros, right? You'd end up with negative 13, that's fine. You can end up with negative values. You can end up with 0 or positive values, fractions or decimals. But anything would work in this type of equation. So don't be fooled that this one is kind of long. What is that, 5 terms right there? The length of it doesn't matter. Again, we're only focused right now, at least, if there is roots, which there is none in this problem, or if there's denominators, which, again, there is none in this problem. Now, do keep in mind in this, just because in the future, if some of you guys choose to take some more advanced classes, they'll ask for range on this, which is a little bit different, okay? But we don't have to worry about that right now. So they give us a function. They said find f of 9, find f of negative 10. Now, if we can find any type of numerical value for either one of these, or both, then it's going to answer the question for both of these, okay? Is it in the domain? Well, let's find out. So I'm going to do f of 9 first. Let's see what we get out of that. So that would be, remember, our function shows 5 times x squared plus 10 all over x plus 10, right? But here, we're saying the x value is 9. So I'll replace my x's with 9s right here. I think that's still big enough to see. There's a 9 and there's a 9, okay? Now, by the order of operations on this one, you know what, I'll work it out. So I'm just gonna focus on the numerator though. So 9 to the power of 2, that'd be 81. And then, yeah, we still got the plus 10. Then I'd do 5 times 81, 405, I think. 405, now plus 10. And that gives 415. Why am I doing this? Because, I don't know, I just kind of felt good about it, but your calculator would do this for you, right? So my numerator is 415. Let's see if that makes a difference. 9 plus 10, that's just 19. Okay, so we get 19s throughout as our denominators on these. 415 divided by 19. I don't think that's a multiple, but I'm going to use my calculator just to make sure that it could not be simplified. Oh, yeah, it cannot be simplified. So we'll just keep it at that. So that would be f of 9. You know, I'll write that out too. This equals f of 9. So when the x value is 9, we get some kind of funky y value. That's still okay. Now remember, is that a real number? Yeah, sure it is. It may not be pretty, but it is a number. And so this one, is 9 in the domain? Yes, it is. Okay. Well, that was fun. So let's try f of negative 10 then. All right, let's look at this one. Same exact function though. So that's a negative. I think I forgot the negative sign out there in the front, didn't I? There was this one right here. I did. So that would have been a negative 415 19ths. Because this is a math class and I got to take my time. So I'm going to do this one. And I think some of you noticed that as well. Now I just tend to work in the numerator, and it's good to have if you have your own, process down like I'm talking about, right? Because it'd say 5x squared, and then that's plus 10 all over x plus 10. Right here, and again, yeah, you could say, well, our denominator is definitely going to be 0 on this one, but I'm going to skip that for now, and I'm going to solve the numerator because I'm a math nerd and I like it. Okay, so that's a negative 10 right there, and then this x also gets replaced with negative 10. So it would be easier to say, well, negative 10 plus 10, right here, it's going to be like a negative fraction with a 0 denominator. And just, again, yeah, maybe some of you guys noticed that. In any case, it looks like the numerator would be 510. 510, okay? But again, you'd say your denominator can be zero. I skipped some steps here, but your denominator cannot be zero. So this one right here, we're gonna, even though it's negative, we don't care about the negative, but this one's just undefined, a D and E type situation. And I believe it will want you to put that in on Canvas, okay? But since it's a D and E situation, it is -10 part of the domain. It is not. So there we go.